What we'll do today is start our discussion of learning Bayesian networks. We have two chapters in the book that are dedicated to the subject, and today we will start with the first one on the maximum likelihood approach for learning Bayesian networks. What we'll see in this chapter is basically methods for learning both the structure and the parameters of the Bayesian network, and under different conditions, particularly what is known, the data that we have and its nature. And in chapter 18, some additional information beyond the data will also factor into the learning process. So let's get started with some basic terminology that would be relevant through our discussion of learning. We've seen this example before from chapter 5 when we looked at modeling. This was an example of a network from the domain of diagnosis. We have conditions and we have symptoms. And in this case, this particular structure could have been developed by hand, but then the parameters of the network may need to be estimated from data. So what is data? And data looks like this. That's going to be the key thing now in the discussion on learning. You have a table. As you can see, the first row here lists the variables that we have in the model. And you can think of every row in this table as a patient, right? So, and what we know about them. So in the first case, we have a patient, yes, they had cold, they didn't have a flu, we don't know whether they had tonsillitis, and so on. And then there is another patient too, and so. And as you can imagine, these rows may have duplicates in them, right? So we have two distinct patients with the same information that we know about them. One key distinction that comes up in learning and influences learning algorithms is whether the data itself is complete or not, right? And that's a very important distinction. A complete data set is one in which we know the value of every variable in every row. So in this case, if we're talking about patients, then for every patient, I have 1, 2, 3, 4, 5, 6, 7 variables. I will know the value of every one of these 7 variables about them. If that's the case for every patient in the data set, then we would say the data set is complete. The more common case, though, is incomplete data, and that is more challenging, as you will see, from different points of view, both statistical and computational. Also going into terminology, sometimes we call these rows observations or units or cases. The whole data set is sometimes called a sample. Then you talk about the sample size or the data set size. There's a connection between that notion and I think chapter 15 on inference by stochastic sampling, which we kind of skipped actually. We'll allude to it a little bit as we go on. All right, so this is the basic terminology. And as I said, our objective is to look at both estimating the parameters of a network structure given both complete and incomplete data set. In fact, that's what we'll focus on today. We will look at mostly parameter estimation techniques under these two cases. And next time we will look at learning the network structure itself. That you can also do under complete and incomplete data, but we will focus only on complete data. We'll mention why later. And that would be chapter 17, which is the maximum likelihood approach. Now, the principle here is to distinguish this from chapter 18, which looks at the Bayesian approach, is the following. In the likelihood or maximum likelihood approach, there's this notion of a likelihood principle which favors those estimates that have a maximal likelihood, i.e., they maximize the probability of observing the data set. So if you give me, let's say, a Bayesian network structure, and you give me a data set, there's two dimensions to the questions of learning. One dimension is what's the right parameters to learn. So in the sense that you take this network structure, and one of you puts some numbers in, and another puts different set of numbers in based on the data set. And we have to look at them and say, which one is better, right? It's kind of a statistical question, regardless of how do we find these numbers, right? So you have to settle first the question of what am I after? What is the objective function I'm optimizing when I'm learning? And the likelihood principle basically says you favor or you choose the guys that maximize the probability of the data set, right? If you put parameters on the structure to get one distribution, let's call it A, and you put another set of parameters and you get another distribution, let's call it B, you can go to distribution A and say, what do you think is the probability of this data set is? For the case of patients, you can go to the patients one by one and compute the probability of seeing each patient according to distribution A. And then you take the product and say that according to this distribution A, that's the probability of seeing this particular data set. And then distribution B will give you a different number, and you choose the one that maximizes that probability. This is basically this principle, the maximum likelihood principle, and that's what we're going to focus on today and next time, which is also the subject of chapter 17. Now, the Bayesian approach, which we will talk about then the week after, which is the subject of chapter 18. You introduce more information into the process of learning. And roughly, it looks like you will have what we would call a meta distribution, which is a distribution over your choices. So if here are the different things I can learn, you will have a distribution over these things, and then you end up picking the guy that has the highest probability. It's pretty interesting, actually. You'll see it when we get to it. You're trying to learn a distribution, but you set a meta process in which the data that you have end up being evidence. And you condition on the data set as your evidence and compute a posterior distribution over the possible things that you could have learned. What is intriguing about it is it's a formulation in which learning becomes, or it gets reduced to inference as we know it. As we discussed inference, exact inference and approximate inference, you can turn the learning problem into an inference problem. And we'll see that when we get to chapter 18. So these are two main approaches. Sometimes people also talk about what they call constraints-based approaches. And the idea here is I try to learn a structure that relates to the data set in a way that it tries to respect the conditional independences that are implied in the data set. So this borders more on the work on causality. We will not discuss this. Actually, it's not discussed in your book. So yet another objective measure. It relates mostly to structures, right? What is the right structure here? Is, again, you think of the right structure as the one that basically mimics the independence assumptions in the data set. So there is another distinction to all of this, all right? So trying to map some of the space in learning and which parts of it we will look at. This dimension is important. When you're trying to learn, there is the question, again, as I mentioned, is what are you trying to optimize? In this regard, there's the question is, what do you want to use the model for when you learn it? Sometimes you know. If we're learning, let's say, network medical diagnosis or prediction network like the one we've seen, you may say, I'm going to use this to do diagnostic tasks. That is, I'm going to be inferring the most likely disease given symptoms. You give me the value of the symptoms, and I try to find the most likely disease. Or you may come and say, no, I'm going to use it for prediction, actually, in the sense that I'm going to actually, you tell me what the disease, and I'll tell you what's the most likely symptom. If you remember from chapter 5, what that means is now I'm fixing the evidence and query variables up front, and I'm telling you this is how I'm going to use the model. Sometimes if that's what you're doing, let's say big diagnosis. Then in that case, you can optimize something more direct. You may have data in which, for particular patients, here's what I know about them, and here's what the real answer is. And then when you try to learn a model, you try to minimize the error in comparison to this data that you have. When you do that, people talk about discriminative learning, right? In a sense, you can think of it as learning where we're optimizing for a particular task. I know what the specific task is. I have a clear notion of error rate, and I want to minimize the error rate as far as the learned model that I have. This is in contrast to what people call generative learning, where I want to do the learning but I want to do it independently of how I'm going to use the model. And then if you're not fixing how you're going to use the model and you're not trying to optimize a certain error rate, then we fall back on basically the principle that we mentioned, that is, you try to really learn the model that best explains the data set, that maximizes its probability. So you've got these two principles. One is task specific, one is not task specific, and each one of them has its own objective function. What we will be doing in both chapters 17 and 18 is generative learning. In fact, let me mention here this discriminative learning. This is what you see, for example, today with neural networks. That's what you optimize. You get labeled data input output, and then the gradient descent methods are actually trying to optimize your error or loss function more generally. All right, let's get started. So we have, as I said, two components today. Both of them are dedicated to estimating parameters. So we're going to assume for now that we know the structure and we're just going to estimate parameters. And we're going to have two methods. The first method is assuming that the data is complete. And you will see that this is a relatively well-behaved case, but it also provides the foundation for the second case. The second case or class of methods is when the data is incomplete. And that will basically be it today. And next time we'll look at learning structure. Now, here's an important concept that will appear in both situations, whether the data is complete or not, which is the notion of an empirical distribution. So we're going to be using this as a running example. We have a network that has three variables: whether someone is health aware or not, whether they smoke or not, and whether they exercise. This is the network structure. They're all binary variables. And this is our data set. You can see the three variables H, S, and E, and I have 16 cases, right? So the data set of size 16, is this complete or incomplete? It's complete. Every row, I know the value of every variable. Now, what's going to be relevant here is this notion of an empirical distribution. What's an empirical distribution? Look at the notation here. PR, the subscript is D. This is data. We use this symbol to represent a data set. All what we're doing here is counting, right? So I have three variables, therefore 8 possible instantiations. Look at the first instantiation. Everything is true, true, true. What's the empirical probability? Just count. How many times did that case or that row appear here? 2 out of 16. If you look at the last guy, everything's false. It appeared only once out of 16. The most common one is what? The most common one is the third guy. Someone who's health aware, doesn't smoke, and exercises. That's a good population. I have 9 out of 16 instances in the data set that look like this. Okay, so this is the empirical distribution. The technique for estimating parameters in this particular case, when your data is complete, is going to be very simple. You can come to it from different angles. I'm going to get to it from the most direct angle, which is estimate parameters based on the empirical distribution. You'll see it's computationally easy to get these estimates, and we're going to spend most of the time talking about their properties. Tightening our notation just a little bit more when we start writing formulas, we're going to use this notation here. D is the data set, sharp is a count. So when I say this, D sharp of H, S, and E, I'm like saying how many times does that particular instantiation appear in the data set. And I'm dividing it by big N, which is the size of the data set. And this would be the empirical probability of that particular instantiation. This could be alpha more generally, which is any event, right? So I give you D sharp of alpha, and you simply count the number of rows in the data set that satisfy that alpha. So we're going to be using this notation, and that would be the formal definition of the empirical distribution. So according to this estimation technique that we're starting with, you simply estimate parameters based on the empirical distribution. What does that mean? You need S given H. This is basically the parameter that someone would smoke given that they're health aware. And according to this guy, you just simply do this. You compute that according to the empirical distribution. That is, you compute the empirical probability of S and H divided by the empirical probability of H. And according to this, you get 1/6. And you can get these estimates by doing a pass over the data set. This is the more general notation I alluded to that we're going to be using and so on. So if you want to compute the empirical probability of any event alpha, you just count how many of the members of the data set or rows sets phi alpha, and you divide that by the size of the data set. Again, tightening our notation, because when we write equations later, we would need to be more principled about this. As we said, this is a data set. It's over a set of variables x. The data set itself will be a set of what we call rows or observations or cases. These are the D1 through Dn. So in general, these are partial instantiations of x. So it's called a case. The data set is complete if these D's are full instantiations of x. So that's the complete data set. If each case is a complete instantiation, otherwise it is incomplete. And here's the empirical distribution. Some more examples to, again, familiarize ourselves more with the notation. Counting how many rows in the data set satisfy a particular alpha for different alphas. Alpha here is a full variable instantiation, right? But alpha could be a partial variable instantiation, like in the second case. We're just saying how many cases satisfy H equals true, 12. It could be an arbitrary event. We're talking about someone who's health aware or exercises. H is true or E is true. How many cases satisfy that event? In this case, it turns out to be 14 out of 16 do that. Okay, so here's our first equation for parameter estimates, putting it officially. We're talking about a given structure. We're talking about a particular variable x with parents u. And we're talking about one particular parameter for that variable. So small x, as you remember, is one particular value for that variable. And small bold u is one particular instantiation of the parents. So this is one particular parameter. What's the estimate of that parameter given a data set? ML stands not for machine learning. ML stands for maximum likelihood. As we discussed, that is simply the empirical probability, which according to our notation is this. We looked at it from an intuitive point of view. We just said, oh, let's look at the empirical distribution and let's use it to estimate parameters. And now we're going to see actually that these estimates satisfy a bunch of interesting properties. In fact, you could have arrived at them, not like the way we did it, but you take some of these properties that I'm going to mention and you say, I want to optimize that property, and you arrive at these guys. Here's our running example again. And here's the estimates according to this equation. That is the ones based on the empirical distribution. Remember, you need the CPT for this guy, that's this guy. You need one for this, here it is, and another for that guy. Again, these were just obtained simply from the empirical distribution. Now, here's one of the properties of these estimates. As you can imagine, these estimates will be different depending on the given data set. They become more stable as the data set size increases. In fact, you can show that if this data set has this particular size and the data set is indeed generated from the underlying distribution, then the distribution over these estimates in the limit becomes normal, right? Tends to a normal distribution that has this particular mean and that particular variance. What does that mean? You have a formula. And you say, I want to estimate. I say, here's a data set of size 1,000. You apply that formula, you get estimates. Let's pick one of them. You get a number. But now I give you another data set of the same size. You probably get a different number. So in a sense, there is a distribution over these estimates. And as n goes to infinity, that distribution becomes or tends towards a normal distribution. The reason I'm showing you this is I want you to see this particular situation here. One is what you would expect. What happens to the variance as the size of the data set increase? Becomes smaller, right? So your estimates become more stable and closer to each other, right? So you clearly want a bigger data set. That makes sense. But look at this guy. What is this? This is the probability of the parents. If the probability of the parents is small, that's not good. If the probability is too small of the parents and the data set is not too large or not large enough, it's not uncommon for the empirical probability this to be 0. That is, you will not see any rows in the data set that satisfy this guy. In that case, this thing is not well defined. You can't compute it, and this is known as the problem of 0 counts. We'll get to that later. This is actually a problem that does come up, and some of the techniques people do for estimation is to actually address this. The Bayesian approach that we discussed in chapter 18 kind of gives a more principled way of dealing with this. Now, this segment will be telling us a little bit more about the likelihood principle and about the estimates that we just talked about. And again, it will provide a bridge to how we're going to handle things when the data itself becomes incomplete, as you'll see in a little bit. So let's more formally define the objective measure that we're after, right? We talked when we started about the notion of the likelihood principle or maximum likelihood principle. Now, the likelihood of parameter estimates, think of it as the quality measure, is like this. Let theta be the set of all parameter estimates for the network structure, right? So this now is a vector, right? All of the parameters of your network. And now we have the network structure G. Now, we would use this to indicate the distribution that is induced when using these parameters theta on that structure, right? So this distribution now is indexed by theta. So if you estimate different parameters, theta prime, you get different distribution. Okay, now, let this be the probability distribution induced by this structure and those estimates. The likelihood of these estimates is the following. This is the notation, and let's look what's going on here. What are we doing? We're going to the data set and iterating over the rows one by one, correct? We're computing the probability of each row and just taking the product. We call that the likelihood of that parameter estimates, and we write it like this. Now, here's our first result. Our estimates that I showed you the equations for were based on the empirical distribution. We didn't justify them, right? We just said, let's estimate them based on the empirical distribution. But they turn out to be the unique maximum likelihood parameter estimates, in the sense that if that's what you're trying to optimize, you are trying to find the parameter estimates theta that have a maximum likelihood, as we just defined it. So you're doing this argmax of theta. You're optimizing this and collecting theta. That's the same as the parameters that are computed according to the empirical distribution. So indeed, using the empirical distribution, in this case, complete data, will give you maximum likelihood estimates, and they're unique. This is important because when we go to incomplete data, you will see that maximum likelihood estimates are no longer unique. You could have multiple sets of parameters that maximize likelihood. Here's another property of these guys. You guys remember kl-divergence? We talked about this briefly when we discussed, for example, approximate inference, belief propagation. And the KL is a number that you compute between two distributions. I give you distribution A, distribution B, and you say, what is the KL divergence? And it is meant to somewhat measure how close they are to each other. And as we said, though, except that it's not a true distance metric, it's well known. Now, these guys that we just talked about, the estimates, look what property they have. If you look at the empirical distribution, right? The distribution that you just get from your data set, and you look at the distribution that's induced by the Bayesian network using a set of parameters theta, you pick up some theta, then it's meaningful to say, what is the KL divergence between that distribution that's induced by the Bayesian networks under these parameters and the empirical distribution, correct? Okay. The parameters that maximize likelihood are the ones that minimize the KL divergence. So now we have three ways to describe these parameters. First, they're simply the empirical probabilities, right? You look at the empirical distribution and estimate based on that. One. Second, they're the ones that, unique ones that maximize likelihood. That is the probability of seeing the data. Third, they are the ones that minimize the kl-divergence between the empirical distribution and the Bayesian networks. They're all the same. And you can see the derivations in your book, by the way. You just take the kl-divergence, unfold it, move things around, and you can see how this corresponds to optimizing likelihoods. They're nice, useful manipulations if you want to see that. There is one more property that we want to say about these things that also requires setting up even more notation. If I give you a data set and I give you a Bayesian network structure, we agreed that the maximum likelihood estimates are unique. If they are unique, then you go find them and you plug them into the Bayesian network. Now you get a distribution. And then now you say, what is the probability of the data according to that distribution? You compute it. That's the likelihood of these parameters. But since these parameters are unique, that likelihood now is a property of the structure itself. So we would write this. We would say, what is the likelihood of that particular structure, Bayesian network structure, given a particular data set? And the meaning of that is, go ahead and find the maximum likelihood estimates for that structure, unique, correct? Plug them in and compute likelihood. So it is this. It is the likelihood of the unique maximum likelihood parameters. We're going to make an observation about this guy in just a second, and we'll use it later when we talk about learning structure. We need to be comfortable with this. This is going to end up being a main ingredient later when we learn the structure of the network. Think about it this way. Given this notion, someone might say, I like this structure. Let's call it G1. Another one says, no, I like that structure. Let's call it G2. With this, now I can ask the following question. If you quantify G1 using parameters in the best way possible, that is to maximize the likelihood of the data, how far can you go? What's the best you can do? What's the best? Maximum likelihood estimates for that structure. You do that, you get a number, which is this guy. And then I'll tell you, okay, for the other contender, G2, the other structure you have, what's the best you can do in terms of optimizing the probability of the data? Find your best parameters for that structure. Those are also the maximum likelihood estimates. You do it. Now you have a score for each structure, correct? Now, in a way, we have a way to start discriminating between structures. Of course, it's not going to be the whole story for structured learning when we get to it, but you can see the relevance of this. This is going to end up being part of the scoring functions when we get to learning structure. Now, the one thing I want to say about this also now, since we're on the subject, we're beating this parameter estimation under complete data, beating it to death now, is a result that will become relevant also when we learn structure, which is this. Well, as usual, I didn't predict right. Not yet. This slide is talking about notation that usually we don't work with the likelihood itself, we work with the log likelihood. So we take the log of that, and we end up getting this formula, and we use LL theta. So this is more convenient to work with for various reasons. So we talk about optimizing the log likelihood, and the likelihood is greater than or equal to 0. Log likelihood is less than or equal to 0. We're talking about log 2, but we just tried that. Okay, this is the result that I wanted to show you, and we'll go over it a little bit slowly. It's pretty critical from a computational point of view. We'll do this, and then we take our break, and when we come back, we talk about incomplete data. Look what's going on here. We're talking about the log likelihood of a structure, as we just discussed it, right? So let's try to parse through this. The whole point of this thing is that the log likelihood can be decomposed into components that depend only on the families, every variable and its parent. So let's look at the notation once more. You have a structure G, Bayesian network structure G. data set D of size n. Now, X is a variable in the Bayesian network structure, and you are the parents. Good? So this guy says the log likelihood of that structure given the data set can be written like this. Look at this carefully. What do you have here? A sum. What is the sum over? Over the families. So if you have a network that have 5 variables, this sum has 5 components. Each one of them is the variable X and its parents U. What does this say? Compute the entropy or conditional entropy of X given U. Based on what? Based on the empirical distribution. Right? This quantity depends only on a family. Aggregate them, multiply by the size of the data set, you get this guy. What's the significance? The significance is you can decompose the log likelihood into independent components. Each one of them relates to a node and its parents. That will be the enabler of key algorithms for doing structured learning later, next lecture, when we talk about that. All right. For reference, the conditional entropy is just this guy. The conditional entropy of the variable X given parents, you basically sum over all possible instantiations of the families and do this. Right? Straightforward. It is one of the essential facts about learning in Bayesian networks is what you're seeing on this slide, which is the log likelihood decomposes under complete data. This is only the case under complete data. Under incomplete data, you don't have this result. So this concludes what we wanted to say about estimation under complete data. The method itself is straightforward. One single pass through the data, you get your estimates. We spent most of the time talking about the properties of these estimates and introducing notation that will be useful later. Let's take our 10-minute break. When we come back, we'll talk about estimating parameters under incomplete data, and in particular, we'll talk about the EM algorithm, which is the core algorithm for this purpose. 10-minute break.